actually, now I can't. Now you have to record, I guess, Felix. Okay. There we go.
Okay, somebody's recording. That's good. Yes, welcome to today's 1W-MINDS seminar. Speaker today is Rachel Ward. As I have read now, she's the Tex Moncrief Distinguished Professor in Computational Engineering and Sciences, Data Science, starting last year, and but has been as an assistant professor and associate professor at UT since 2011. Before that, she spent some time as a postdoc at the Courant Institute at New York University and did her PhD in Princeton under the supervision of Ingrid Dubuchy. And now, like moving backwards in time, she started with her bachelor's at UT, where she's now back. She has a lot of awards. I think I cannot mention them all today, but I would just point out the NSEF Career Award, the IMIA Prize in Math and its Application, and the von Neumann Fellow at the IAS. Should just name a few, but there's many more, and of course you can find all that online. But for that now, that should be enough, and I would thank Rachel for accepting our invitation and looking forward to the talk on function approximation via sparse random features.
Thank you, Felix. Thanks to all the organizers. I'm happy to finally give a talk in the seminar. I had been looking forward to talking last semester, but I was scheduled for, I think, 2 days after the election in the USA when things weren't resolved yet, and I literally couldn't do anything except stare at the news. So I had to cancel, but here I am. I'm going to be talking about some new work joint with several co-authors, my great co-authors Hayden Schaefer and Zhang Tran. I think I see Zhang here, so that's exciting. And also Abafazal Hashemi, who's a postdoc at UT Austin, Robert Shi, grad student at UT Austin, and Ufuk Topçu is a faculty colleague at UT Austin. So function approximation via sparse random features is the topic. What we want to do is sort of have a flexible framework for approximating high dimensional smooth and structured functions where we can incorporate or promote sparsity in the form of smoothness and low orderness of the function, while having flexibility to use bases beyond tensor products of orthonormal polynomials. And so that's the overview of the talk. So let's talk about precisely what the setup is. Also, at any time, please feel free to ask me a question on chat or speak up. I'm always happy to answer questions. So the goal is to approximate a given function from a set of samples. We have m samples, and for theory, let's assume the samples are drawn from some common distribution, and the observations that we observe, as is often the case in real life, can be a little bit noisy. We can have a little bit of noise on the observations. So we observe yk equals f of xk plus possibly noise, and we want to learn a good approximation of the underlying function as a linear combination of a set of n fixed features, which are functions. And so the goal is we have the features, we fix the features, and we want to learn a good coefficient vector C, or a good linear combination of these features, such that we can get some call approximation bounds, which is like L infinity norm bounds between F and this approximation, or in the machine learning world, generalization error bounds, which is like an L2 norm function, L2 norm error bound. So that's the goal for a wide class of structured functions. So what's a good choice for the features and how to learn the coefficient vector in a robust and consistent way? These are some questions, although not all the questions. So I'm just repeating the problem statement from the last page up here. I'm just repeating that here. We're given these samples and we want to find this. There's the compressive sensing approach to this problem. So some aspects of the compressive sensing approach to function approximation, high dimensional function approximation, is that the dictionary or the features are fixed and deterministic and very structured, often taken to be orthonormal polynomials in the one-dimensional setting. In the higher dimensional setting, dictionary basis functions are formed as tensor products of the univariate polynomials. Okay, so could be orthonormal polynomials, algebraic polynomials like Legendre polynomials, or trigonometric polynomials. And a key feature of the compressive sensing approach, which sort of was one of the main innovations of the idea of compressive sensing for function approximation, is that the number of samples that we observe M of the function can be quite small, and we can still get some approximation bounds, even if the function is high dimensional. And the number of samples N in the feature basis is taken to be much larger than M. So we'll call this the overparametrized setting. And because compressive sensing operates by regularizing via an L1 norm or L0 norm type penalty on the coefficient vector C, sort of the resulting function approximation, if the basis vectors are weighted appropriately, can avoid overfitting the samples, even though capital N is much greater than little m. Okay, so these are just a few papers giving some foundational results in compressive sensing in general. If you are not aware of that, you're young, don't know what compressive sensing is. Something that I promoted with Holger Rauhut a decade ago or so, and several people have improved on our function approximation results since then. But we sort of showed that the compressive sensing result, compressive sensing works for high dimensional function approximation in the following sense. Properly weighted sparse orthogonal polynomial expansions can recover high dimensional functions, give good approximations to high dimensional functions, which are in a certain class where the functions are smooth and also low order. By low order, and I'm going to come back to this later on, what I mean is the function seems like it's a high dimensional function. It's a function of D variables, but it hasn't, there's an underlying decomposition of the function into a sum of K functions Gj, J1 through K, which are each only depend on a small number of the coordinates, Q, at most Q, and each Gj is smooth. So this is what's a order Q function. Okay, so the idea is that for functions that are approximately of this form, the expansion with respect to a orthogonal polynomial basis will have fast decay because of the smoothness assumption, and the fast decay of the polynomial coefficient is closely related to sparsity. And then the low orderness is a very direct form of sparsity, that the L1 minimal coefficient solution will pick up those tensor product orthogonal expansions coinciding with the support of the low order functions. And so that's the structure. We do not have access to the sequence of functions Gj. So the magic of compressive sensing is that we don't have to assume we know what these important coordinates are a priori. We assume that Gj is very smooth or well approximated by polynomials up to a certain fixed order. And then by properly weighting tensor product orthogonal polynomials, the solution of minimal L1 norm coefficient and this in the basis will give a good approximation. Uniqueness of Gj is a whole other situation, but that doesn't really matter because we can just assume that this is the sort of capital K, smallest possible capital K. Representation. Of course, this isn't going to be unique, but perhaps for sufficiently small K, it is unique, at least with the support sets. And so this is what I call function approximation with weighted L1 minimization, is in the area of uncertainty quantification called sparse polynomial chaos expansions. And then this has been studied and enhanced a lot and tailored to different types of function approximation goals over the past 10 years. So some of the limitations, I would say, of this approach is that there's a lot of things that have to be set just right for this whole machine to work. First of all, the underlying function must be well represented by polynomials. It can't be like a rational function. One of these GJs can't be a rational function, can't have any asymptotes. One needs to orthogonalize the orthonormal polynomial basis with respect to the probability density for the random samples. So the form of the feature basis is a function of the distribution of the sampling points. And so that's tricky practically for getting that right. Another tricky thing is that orthonormal bases of tensor products of univariate polynomials is a very cumbersome high dimensional basis to construct. Not only is it cumbersome, but once you construct the exponentially many products of tensor products of univariate polynomials, you have to prune that basis according to retaining only those on certain hyperbolic crosses or lower dimensional sets in order to have a dictionary that's not exponential in size, a dictionary that's tractable to put as an input to an L1 minimization problem. So these are all some challenges of this compressive sensing approach. A more recently exploding in popularity approach for function approximation is the neural network approach. So let's see. So just for one slide on the neural network approach, one slide summary for this talk. A two-layer neural network, of course we can talk about deeper neural networks, but a two-layer neural network, you can think of it as solving for both a good set of coefficient variables and also solve for a good set of feature functions themselves starting from with parameterized class of features. So you want to optimize not just for the coefficients in the expansion, but also optimize these weight vectors in the feature basis. So you're also moving around and changing the functions, the feature functions, and the biases. Okay, and so this makes the optimization problem, as opposed to L1 minimization, which is convex, this joint optimization in optimizing the form of the functions and the linear expansion with respect to those functions make the optimization problem non-convex and more complicated. And so in practice, these are optimized via least squares, not L1 minimization. So we have nonlinear data-dependent basis functions when we do function approximation with neural networks. And this can be a good thing. It could also be a bad thing. It could be a good thing because we're using more information in the data at hand, but we could also overfit the particular data. And we also have to retrain such a neural network every time we're in a new situation with new samples, which is they're theoretically icky. So the least squares optimization problem resulting in neural network function approximation is non-convex because we're also solving for the features themselves, not just the coefficient. So there's some recent work that shows that in the very over-parameterized regime where capital N is much larger than little m, shallow neural networks, over-parameterized neural networks, are still optimized exactly via least squares, meaning an exact function interpolation can be obtained. So a neural network function that exactly interpolates the samples at hand can be obtained even though you're doing a non-convex optimization problem. So that's a lot of recent analysis there. So that's very nice. However, there are still some critical limitations of this approach from a theoretical perspective. Solving the non-convex least squares optimization problem to find an exact function interpolator of the data does not say anything about the generalization error of the resulting approximation, which the compressive sensing type results have. Remember, generalization error is like an L infinity norm error bound between the function and the approximation, or L2 error bound. Also, the least squares minimization, which is what's used in neural network approximation, does not promote sparsities. We couldn't take advantage of, say, low order structure in a high dimensional function, or smoothness in a high dimensional function. You can't take advantage of it in a theoretically tractable way like you can with compressive sensing. So we were looking to try to find the best of both worlds framework for function approximation, trying to draw on the advantages of both the compressive sensing and the neural network approach. Focusing on the setting of scarce data. So when the number of samples M of the function that we have is limited, somehow small. So I'm not talking about the setting where we have a lot of training data, where neural network is obviously going to do better than a compressive sensing approach. So the hope is to overcome the limitations of the sparse approximations, like the cumbersome aspect of building these high dimensional orthonormal polynomial bases, but still get theoretical guarantees on the approximation accuracy. We want to get constructive accuracy guarantees. In neural networks, one often just has non-constructive accuracy guarantees, the proofs of existence of some set of parameters such that a function approximation is good. We want an algorithm and a guarantee for the parameters that result from that algorithm. And again, we focus on the data scarce regime where the number of samples is small. Okay, so what we want to look at is doing compressive sensing or L1 minimization basis pursuit type algorithms, but not with a deterministic feature basis of orthonormal polynomials, but with random feature basis, a random feature basis. So this is motivated by the random features approach of Rahimi and Recht, which was originally promoted for a fast approximation of large scale kernel matrices. More recently has found interest in terms of just function approximation, which is a little bit different setting. And the idea is that for the overparameterized shallow neural networks, even though the weights are parameters that are optimized in the neural network, at initialization, the weights are randomly initialized to be Gaussian random vectors. And the recent work on neural network theory showing that training error can go down to 0, the point of that theory is that these weights don't move that much from their random initialization. And that's how they can show in this overparameterized setting that neural networks can be trained to have 0 loss. So we thought, let's just randomly draw the weights in the random features and then fix the weights. If they don't change that much in a general neural network setting, then let's just not change them. So again, we're looking at random dictionaries or random, not orthonormal bases. Like random Fourier features are going to be what we focus on for the theory here. So if we draw a bunch of feature functions by taking vectors of weights according to a multivariate normal distribution centered at 0 and with variance sigma squared, then the resulting set of functions can be thought of as like a randomized high dimensional Fourier system. So instead of the orthonormal basis approach where the weights are on a grid in high dimensional space, and then that grid is pruned down according to a hyperbolic cross structure, we just consider random frequencies. Are they normalized? I don't really understand the question. Is what normalized? The weights normalized. The weights are drawn as spherical Gaussian vectors with variance sigma squared. Is the pruning very difficult, computationally inefficient, or what's the problem with hyperbolic cross points? That's a very good question. Let's see. A couple answers to that question. One is it's not very appealing to consider that you have a certain basis and then you throw almost most of the basis elements away, except those on hyperbolic crosses. I would say it's computationally cumbersome. The other advantage of random features is just a more general advantage, which is going from an orthonormal basis to a redundant dictionary, where we can increase the redundancy as we wish by simply drawing more and more features. Having redundancy in the basis, it makes the theory more difficult, but what we find empirically is that it allows us to get good approximation to a richer class of functions than those we can approximate with tensor products of orthonormal polynomials. And I think that's due to increased redundancy in the basis compared to an orthonormal basis. So the random Fourier features is what we have theory for right now, but very closely related are random trigonometric features and then random activation features, which correspond to the rectified linear unit activation, which is the most popular nonlinear activation for neural networks in imaging applications. So again, this is just the basic function approximation problem we want. And we're going to form a feature basis for the function approximation by drawing random basis elements from this parametrized family. We can think of phi as being the complex exponential, e to the I inner product x omega j. And these are like two-layer fully connected neural networks at initialization when the weights are initialized randomly. We're just going to consider that as our basis, the neural network at initialization, and just optimize the coefficients Cj. And of course, sparse optimization, we want to regularize the coefficient vector C with L1 norm or L0 norm penalty, unlike in the neural network setting where it's optimized with an L2 least squares type of optimization, because we want to promote sparsity. We know that a lot of functions of interest in the real world are well approximated as being smooth and being low order functions, just based on the sparsity of effects principle, which says that a lot of natural phenomenon are well approximated by a small number of low order interactions. And we want to have interpretable results. Sparse coefficient vectors are interpretable. They tell us these are the important features, these are not. So our sparse random features algorithm is as follows. We first initialize a parametric function that we're going to draw random instances from for our random features. We set a stability parameter for the basis pursuit optimization problem later on. We draw M data points according to a probability distribution and observe the noisy measurements, noisy function evaluations. Then we draw capital N random weights from a spherical Gaussian distribution with variance sigma squared and construct our random feature matrix, which consists of the capital N different random features evaluated at the little m number of sampling points. And then solve for a function by solving for a set of coefficients as the minimal L1 norm coefficient vector, which fits the observed data points yk up to the accuracy eta, which should be a function of the noise. So if noiseless, then eta can be 0 if the measurements are noiseless. And the output is a function, which is a linear combination of the random features. And we want to say that within a certain region, this function is guaranteed to have a certain L infinity norm error or uniform approximation bounds to an underlying function. So let me know if you have any questions on the algorithm. Okay. So analysis, first of all, what class of functions does this method work well for? How do we deal with high dimensional inputs, and what types of accuracy and complexity bounds hold for the sparse random features model? How do we avoid the curse of dimensionality and sample complexity by exploiting sparsity? They decided to mow the lawn right now, of course. Sorry about that, if you can hear the lawnmower. Okay, so the natural function space for analyzing random feature models are these are the following types of classes. How do I decide the quality of approximation? L infinity norm bounds. That's what I'm going to get to. Does that answer your question? At this point, the weight vector is just d-dimensional. So d-dimensional spherical Gaussian, where d is the dimension of the input. So hopefully, let's get back to these questions when I put the exact theoretical results we have. I think it'll be a little bit easier to talk about it then. So the function space is, we're going to try to prove bounds for functions in sort of reproducing kernel Hilbert spaces generated by the parameterized feature class. So we look at functions which can be written as an integral with respect to the random feature parametric form. And the functions need to be bounded with respect to rho, where rho is the density that we sample random features from. So if you think of rho as a multivariate normal distribution and the phi as the complex exponential, then this is basically the Fourier transform representation of a function. And asking that this rho norm is bounded is asking that the Fourier transform of our function is almost essentially band limited. It decays very, very quickly outside of a ball of radius, approximately the standard deviation of the density that we sample the random features from. So this is a very strong model. This is asking for functions that are very smooth, essentially band limited, high dimensional band limited functions. I'm going to get back to making this model less strong later, but at present, I'm just trying to emphasize that. And this is a natural class when our feature basis is random features, because drawing random features from this phi class according to density rho is like doing a Monte Carlo approximation of this integral. Sorry, this should be alpha divided by rho here. If we draw the features according to rho, then we're doing a Monte Carlo approximation of the normalized integral, alpha divided by rho phi, if we sample according to rho. So that's why it's a natural, there's a natural class. However, the difficulty in the theory is that this approximation here is an existence type of approximation. It says that if you draw a number of random features according to the density and alpha divided by rho are bounded, then this will hold, except these alphas are not known to us. There's just the existence of some alphas, alpha WK. And this is why when random features were proposed, Rahimi and Recht were able to give non-constructive approximation, function approximation guarantees for random features, non-constructive approximation results of this form, saying there exists a set of coefficients alpha basically the alpha omega 1 through alpha omega n, such that we had this approximation of something. So the novelty in what we're doing now is we're not just saying there exists a good function approximation using random features, but we're going to show that the minimal L1 norm coefficients, according to our sparse random features approach, will give a good function approximation. So constructive versus non-constructive results. Okay, and this class is related to Barron function class used in neural networks. The Barron function class is not as strong. It doesn't ask for as much smoothness, but it's just related. And we're going to get approximation guarantees that are like 1 over square root of n, where capital N is the number of random features that we draw. So the first result that we have, this is not the result, this is just the setup. Okay. Suppose that there's an underlying function in this bounded row norm class. And I'm sorry, by this row, I meant to write normal mean zero variance sigma squared times the identity. Okay, that is the row. So I meant to put that there. So according to the previous slide, F has bounded norm. And suppose the random feature class is the exponential, so that the row norm is basically a band limited assumption on the Fourier transform, or band limited function on the assumption on the function. Then suppose we get a number of data points x1 through xm that are drawn independent from a common distribution normal with mean mu and variance gamma squared identity. Okay, so suppose our m sampling points are drawn according to a Gaussian with mean mu and sampling variance gamma squared identity. We don't have to know mu. We don't have to know gamma squared either. Then we draw our random features also from a normal distribution with mean zero and variance sigma squared identity. So sigma is a parameter in the algorithm. And then we form the random features matrix and solve the basis pursuit problem with respect to this finite matrix to find the coefficient vector of minimal L1 norm solution up to the noise level prescribed. Then the result we have is we have an explicit range of parameters such that we can get a uniform approximation result between the underlying function in this class and the function that results from the sparse random features algorithm. So it's a little bit technical, but this is an explicit non-trivial range of parameters. The most interesting condition is that we found that the variance from which the function samples are drawn, the standard deviation of the samples in time and the standard deviation of the random frequencies and frequency space has to satisfy an uncertainty principle. Sigma squared, gamma squared has to be greater than or equal to this critical lower bound. S is a sparsity parameter that we have as an input, which is down here in our function approximation result. We get a bound on the best S sparse approximation to this underlying C star coefficient vector. And the C star coefficient vector is the vector that Brahimi and Recht showed exists in their function approximation results with random features. So C star is sort of these alpha over rho values, which are not known, which are just in response to the random features we draw omega 1 through omega n. So if that is a very highly compressible vector, then this is going to be small. And then we get a bound on the number. We have to draw a minimal number of random features and a number of measurements, which is much, much smaller than the number of features, as is the usual compressive sensing setting. And then with high probability, we get an error bound of this form. And so a couple questions are, when would this coefficient vector C star be sparse? This is a data sparse regime. Yes, the number of measurements, capital M here, is in its dependence on capital N, only logarithmic dependence in capital N, the number of features. Its dependence on D, the dimension, is not great. And we're going to address that in the next 2 slides. When might this coefficient vector C star be sparse? It should be sparse or approximately sparse for functions whose Fourier transform is not only approximately band limited, but also exists on some small dimensional, or is localized to some small dimensional domain. And we just don't know what that domain within D-dimensional space. So it's supported on a lower dimensional set within D-dimensional space, and we just don't know what that set is. So it's localized in frequency. Josh asked a good question. He says, how much does the result rely on the fact that the original distribution for the X's is Gaussian? Does it extend to sub-Gaussian? When we started this project, we thought that we could make the X's anything. That was the hope, that we could say something about fewer restrictions on the distribution of the sampling points than in the compressive sensing bounded polynomial system case. Right now, for this theory, we need the X's to be Gaussian. The omegas, strangely, do not have to be Gaussian. The omegas can be sub-Gaussian or even uniform. We have a version of this theorem for uniformly drawn frequencies. So there's a deterministic condition on the frequencies that they're a sort of classic approximation theory condition, that they're not too close together, and they're not too far apart. But for some reason, the theory we have, the X's have to be Gaussian.
Rachel?
Yeah.
Yeah, so on the same note, I had the question earlier as to what metric you evaluate the quality. And so if one does machine learning, there is a data distribution, and then the error is measured with respect, it's typically the expected value with respect to that same distribution. And so here, what is surprising is, well, first of all, it's not clear how the theorem depends on dx. Second, there is a mismatch between the original distribution of the data and the final result here, which is the supremum on a ball of radius r. And so what can happen is, for example, that this is really a worst case bound. So it could be for an X that has a very low probability.
What was the last thing you said?
That is a worst case bound, and so it could happen for an X that has very low probability.
It could happen for an X. I can't tell if this is a critique or a compliment. Sorry, it's probably Zoom fatigue.
Yeah, I guess I'm trying to understand why the error with respect to which one evaluates the quality of f sharp of X isn't related to the way in which the data is generated in the first place, that the distribution of the data should play a role in the way in which I evaluate the quality of the approximation.
Well, so first of all, there's a typo here, that this should be a ball centered at mu, the center, where the X's are drawn according to a normal distribution centered at mu. This ball, a radius where we get approximation, should also be centered at that mu. That's first of all, that's a typo. Second of all, the condition in the uncertainty principle sort of is a necessary condition on the way the points are sampled, such that we can get this guarantee. Only if the points are sampled from normal distribution with large enough variance can we get this bound. And the variance is constrained sort of there's a dependence between the variance and the radius, capital R, in the number of samples M that are needed. So I don't know, we were targeting the whole time to try to get an L infinity norm approximation bound. So there might be something better with something like you're mentioning, but we were sort of focused on the goal of a L infinity norm bound. So just to move things along, sort of the punchline is that we can do a lot better if we assume that our underlying function is not only smooth, but also low order. We can do a lot better in terms of our guarantees and their dependencies on D, the dimension of the underlying function. So just to repeat, an order Q function, we got this definition from these researchers from a decade ago, although there are several different names for this type of function. There's additive function, or higher order additive function is another thing, but it's a very natural high dimensional function. Is called an order Q function of at most k terms. The idea is that Q is much, much less than D if the function can be written as a sum of k functions of the form G sub j, which depend only on at most Q of the coordinates. Okay, so for example, f of x equals x1 plus x2 plus x3 plus x4 is an order 1 function, because it can be written as 4 terms, each only involving 1 coordinate. And now note that in the previous results, our accuracy guarantees were in terms of this row norm of the underlying function, which is a uniform bound, weighted bound on the Fourier transform, which was a very strong assumption, especially for high dimensional functions. So we have to add additional structural assumptions behind smoothness to handle the curse of dimensionality. That's just necessary. It's known that smoothness alone is not a strong enough model to avoid the curse of dimensionality for high dimensional function approximation. And so asking that our function is not only smooth, but also has low order structure. We don't have to know the GJs in advance, just that it is a low order. I think that's a nice balance between structure, a nice added structure to smoothness to give good approximation bounds. And this same model was used in the compressive sensing based high function approximation with L1 minimization. So we're going to incorporate the side information of low orderness in terms of changing our random features. And this is sort of the biggest innovation of this work, is that we're going to encode the assumption that our underlying function is order Q by having a dictionary, not of dense random features, but sparse random weights. So just the same like complex exponential features, but now instead of dense random Gaussian random weights, we're going to draw weights that whose sparsity is small, say ideally a sparsity level Q that matches the order of the underlying function. And we're going to draw random features on all of the D choose Q subsets of size Q. When Q is 2, that's only D squared subsets, so it's not intractable. And Q equals 2 is quite important special case. So the low order sparse random features algorithm is the same as before, except now instead of drawing dense random feature functions, we draw sparse random feature functions, in the sense that we draw our random Gaussian weights to be Gaussian, but only with sparse support, sparsely supported on, and we draw a little n number of them on each of the D choose Q support sets of size Q to sort of fill up a rich, redundant dictionary on all of the whole space. Then we do everything else. So constructing these sparse random features is akin to constructing a hyperbolic cross type structure of tensor products of orthonormal polynomials. The difference is that this is easier, at least for order Q equals 2 or Q equals 3 and D not very big. This is easier to construct this basis in MATLAB. You just norm rand a bunch of different random frequencies, and that's your basis. And it also has the flexibility of being able to increase the redundancy in a sort of uniform way over all the features by increasing little n. And so if we assume that our underlying function is low order and we define this new norm, here I call G, but it's just the maximal row norm over the k different possible GJs. If GJs are the functions in the hidden low order expansion of F. Then we can have similar guarantees, except now our uncertainty principle or our restriction on a lower bound on the frequency variance of the weights versus variance of the sampling points is a much weaker assumption. Actually, that's not true. It's not weaker, 1 over Q instead of 1 over D. But everything else is weaker. We have number of features has no dependence on little d anymore. We just have a number of features that has to scale with Q. And the number of measurements also now does not depend on D, the underlying dimension. The number of measurements we need just is exponential in Q. So this is really in the data scarce regime. This is not very many measurements at all. And then our uniform approximation guarantees are hold with respect to this function norm, which is a much weaker norm than the previous norm, which required sort of band limitedness in all of RD. And this is just smoothness of these much lower dimensional functions, G sub J. So it's a much weaker norm. And then in the data scarce regime, we can compare the sparse random features algorithm for approximating functions with low order structure, like this function. This is an order 2 function because each term just depends on two coordinates. And we see that the sparse random features, and especially the sparse random features, using the low order random features gives much better generalization error than a neural network with the same size features, number of features. This was a 2-layer ReLU network using 500 and 5,000 trainable parameters.
Can I ask a quick question about that plot? Just was that
Sure.
the test error or training error or a
Test
validation error or?
Test error.
Oh, okay, thanks.
Oh, sorry. And then we can also compare to the sparse polynomial chaos approach. And this comparison shows how robust the sparse random features algorithm is with respect to the sampling distribution of the XKs, of the sampling points. And we see here, this is just a commonly used low order function called the Ishigami function. And we see that the sparse random feature model has low error for both samples from normal and uniform distribution, even though we don't have theory for the uniformly distributed samples. So in practice, it's more flexible with respect to sampling distribution, but in theory, we don't have that compared to the sparse polynomial chaos model, which, remember, the polynomials are constructed according to your orthogonalization measure of the samples. So it's going to be more sensitive to the distribution of the sampling points. Oh, okay. So I think this is just terminology. The test error is the sup norm error. When I say test error, I mean sup norm error. I guess test error is usually the L2 norm instead of L infinity norm. Is that the difference in terminology? Test error equals error in new data. I see. So test error would be with respect to data that's itself distributed like a Gaussian, I guess, is so no, in that sense, it's a soup norm. But I don't think that the two should be that different, because a soup norm error in a ball of radius r is going to be sort of quite similar to the test error of points generated from a Gaussian with standard deviation r, I think, something like that. And then these are just more examples of relative soup norm error for approximating various functions, which are all low order functions. And in red is the exact order of the function. So this is an order 2 function. This is an order 5 function, and so on. And we see that the sparse random features with low order features does sort of give the best error results when the sparsity of the features matches the order of the function exactly. But if the sparsity of the random features is taken to be smaller than the order of the true underlying function, often it's not that bad. I mean, I guess now that I'm looking at this, it's sort of bad. But I guess not bad if the sparsity of the random features is taken to be larger than the order Q of the function. Okay, fine. That makes sense. Of course, that should be true. All right. This is just another comparison of this would be training and test errors, because there's not a hidden underlying ground truth function here. This is just high shot data. So there's not a ground truth function to compare to. So here, of course, we use the test error on a set of holdout function values. And we see that the sparse random features using ReLU features or sign features will give much better error for various numbers of features than a dense or a random Fourier features with L2 norm regularization, as well as the ReLU network, where the weights and the coefficients are trained with L2 regularization. And again, this is in the data scarce regime. There's not a lot of data. There's not a lot of data here in this particular data set. If there were a ton of data, then a neural network would do better.
Can I ask you, what is the N equal to?
N is the number of sparse random features that are used in the feature basis.
Okay.
Or in the
really...
ReLU network, it's a number of trainable parameters. So it's just the number of trainable weight vectors in the ReLU network.
But for the neural network, it's fixed at. Oh no, that's increasing with it. Okay, I see.
Yeah, so it's the width. It's the width of the network.
Right. Okay. Thanks.
Yeah. Thank you. That's a good thing to clarify. Okay, so just to sort of finish up, after we posted this work, we became aware of a paper that had a similar spirit from last year called Additive Function Approximation in the Brain, where it was these sparse random features were also proposed, where the randomly drawn weights and the features are drawn on sparse support sets. Targeting in particular additive functions, and they had a neuroscience perspective showing that these sorts of features naturally correspond to the way our neurons connect in our brains, so sparse connectivity. And of course, in the way neural networks are implemented in practice, one implements a convolutional neural network where there are sparse, the weights in the random features also have sparse support, just fixed support corresponding to local regions in the image if we're doing image recognition. So some sparsity in the weights is needed in order to overcome the curse of dimensionality. And so we're just giving some theory for that, also incorporating L1 minimization. Because for high dimensional function approximation, low order functions are very natural. And so one should use an L1 norm penalty if possible.
Question on that last result. Do you have a comparison between the sparse random and the non-sparse random? Not with the neural network, but just the comparison between those two.
In some of these, so for example, in this first here, this dashed one is non-sparse random features with L1 minimization. And the solid one is sparse random features with the sparse weights as well. Where the sparsity in the weights is 2 to match the order of the underlying function. Does that answer? We see similar things like this. So if you have a low order function and you have sparse random features whose sparsity matches that order, you can get significantly better. Is that what you were asking?
Okay, but so you don't, so those are still SRF. You don't have like the full dense random vector.
No, I think the problem is terminology. Sparse random features, we were referring to the L1 norm penalty on the coefficients, but these are dense random features. These are dense random features, minimal L1 norm coefficient norm. And these are sparse. Okay. It's not the best terminology. I apologize for that. Sparse low order random features is this. Sparse random features is this.
Okay, I see. So yeah, that makes sense. Is this kind of like early stopping on neural network training, because it's basically kind of like a neural network where you just stop the training early and you don't change the first layer much.
Yeah,
cool.
You don't change the first layer at all. To be precise. Yeah. That's right. So okay, so there's still lots of questions. There are a lot of follow-up questions here. In practice, how to choose the variance parameter sigma in the Gaussian distribution in the random features. The results are sensitive to sigma squared, the variance. So that's an interesting question. Of course, how to get rid of the assumption that the sample function samples are Gaussian distributed. We see empirically and theoretically that structural conditions can be included through the sparse support selection for the features. They give better function approximation results for low order functions. And this is a new sort of way of thinking about sparse approximation, leveraging successes from the neural network community. A general open question for you to think about if you have some Zoom meeting you don't want to be in, how to approximate a general high order or a general smooth function by a low order function. We have approximation by polynomials, and quadratic polynomials are order 2 and so on. But just what about approximation by low order functions, not low order polynomials? And of course, we have these representation theorems like the Kolmogorov-Arnold theorem that says that any multivariate continuous function can be written as a finite composition of continuous functions and a single variable in the binary operation of addition. So this is a low order function in here. And so any function can be written as a sum of functions of low order functions. So sort of just describe approximation guarantees for general functions in terms of lower functions. That's just a question, but that's the talk. Thank you.
Yes, thanks a lot. So we already had a lot of questions during the talk. Are there more? Feel free to speak up at this point and directly address the speaker.